What if I told you that there could be a pathway to another galaxy, one that does not involve traveling at the speed of light? Imagine bypassing the vast empty stretches of space, arriving at distant cosmic shores in mere moments. This isn't just science fiction. It's the mind-bending concept of a wormhole, a theoretical shortcut through the very fabric of our universe. For generations, wormholes have fascinated scientists, writers, and dreamers alike. They promise a universe far more interconnected than we currently perceive, challenging our understanding of distance and time. But just how feasible is this incredible theory, and could it truly serve as a shortcut to another galaxy? In this video, we're going to embark on an epic journey. We'll delve deep into the science, explore the mind-boggling possibilities, and consider the profound implications of wormholes in our universe. Get ready to have your perception of space and time stretched to its limits. This is a cosmic adventure you won't want to miss. Wormholes, first theorized by the brilliant physicist Albert Einstein and his colleague Nathan Rosen in the early 20th century, are not just a figment of imagination. They are theoretical passages, or bridges, through the very structure of space-time itself. Imagine space-time as a vast, flexible sheet. A wormhole would be like folding that sheet and poking a hole through it, connecting two distant points directly. Think of a wormhole as a cosmic tunnel, a shortcut that dramatically reduces the travel time between two separate points in the universe. This makes the immense distances between celestial bodies, even entire galaxies, seem far less daunting. Imagine being able to travel from our home, the Milky Way galaxy, to an entirely different galaxy in a fraction of the time it would take via traditional, light-speed limited methods. It's a concept that redefines interstellar travel. The formal name for these theoretical structures is an Einstein-Rosen bridge. This term highlights their origin in Einstein's groundbreaking theory of general relativity. While the mathematics allows for their existence, the physical reality remains elusive, a tantalizing mystery waiting to be unraveled. To truly grasp the concept of wormholes, we first need to understand the fundamental nature of our universe. Space and time are not separate entities but are inextricably intertwined, forming a single, four-dimensional continuum known as space-time. This cosmic fabric is not rigid, it's dynamic and responsive. The presence of mass and energy warps and curves this space-time fabric. Think of a bowling ball placed on a stretched rubber sheet. It creates a dip. This dip is what we perceive as gravity. The more massive an object, the greater its gravitational pull, and the more it warps the surrounding space-time. This warping is the key to understanding how wormholes might theoretically form. In theory, extreme gravitational forces could warp space-time so intensely that it folds back on itself, creating a tunnel. This tunnel would then connect two distinct regions, potentially across vast cosmic distances. However, the concept remains purely hypothetical at this stage of our scientific understanding. No one has yet detected a wormhole in the universe, despite their potential existence being rooted firmly in the complex equations of Einstein's general relativity. The mathematical models are compelling, suggesting that these cosmic shortcuts are not impossible within the framework of our current physics. Yet, the leap from theoretical possibility to observable reality is immense. Scientists continue to search for any indirect evidence that might hint at their presence. But what about the practicalities of using a wormhole, even if they did exist? This is where the theoretical challenges truly begin to mount. If wormholes were to naturally form, current models suggest they would likely be incredibly unstable and fleeting. They would snap shut almost instantaneously, making them impossible to traverse. Imagine trying to run through a tunnel that collapses the moment you step inside. This instability makes them extremely difficult, if not impossible, to navigate safely. To keep a wormhole open long enough for anything, even light, to pass through, something extraordinary would be required. This is where the concept of exotic matter enters the picture. Some scientists postulate that exotic matter, a type of matter with very peculiar properties, specifically negative energy density, might be necessary to stabilize a wormhole. Unlike normal matter, which has positive energy density and creates attractive gravity, exotic matter would theoretically exert a repulsive gravitational force. This repulsive force could act as a kind of scaffolding, propping the wormhole open. However, this exotic matter remains purely theoretical. We have no known examples of matter with negative energy density in our current understanding of physics. While some quantum phenomena, like the Casimir effect, hint at localized regions of negative energy, creating it in sufficient quantities and sustaining it to stabilize a wormhole is a monumental, perhaps impossible task. It's a fascinating concept, but one that pushes the very boundaries of what we know about the universe. Given their theoretical nature and the requirement for exotic matter, how would we even begin to detect a wormhole? The challenge is immense, as they wouldn't necessarily emit light or other conventional forms of radiation. Scientists would have to look for indirect evidence, subtle clues in the cosmic tapestry. One potential signature could be gravitational lensing. If a wormhole were present, its extreme gravitational field, even if stabilized by exotic matter, would bend the light from distant objects in unusual ways. We might observe distorted images of galaxies or stars that don't fit standard gravitational lensing patterns. This would be a truly unique optical anomaly. Another possibility involves looking for unusual radiation signatures or gravitational wave patterns. The extreme conditions around a wormhole's mouth might generate unique emissions that our advanced telescopes or gravitational wave detectors could pick up. However, these are highly speculative, as we don't fully understand what such emissions would look like. The current generation of telescopes and observatories, like the Event Horizon Telescope, which imaged a black hole, are pushing the boundaries of what we can see. Future technologies, perhaps even more sensitive gravitational wave detectors, might one day offer a glimpse into these elusive structures. But for now, the search continues in the realm of theoretical physics and mathematical models. The true allure of wormholes lies in their potential to revolutionize interstellar and intergalactic travel. The distances in space are simply staggering. Even our nearest star, Proxima Centauri, is over 4 light-years away. Traveling at the speed of light, it would take 4 years to reach it. To reach another galaxy like Andromeda would take millions of years. Traditional space travel, even at speeds approaching light, makes intergalactic journeys practically impossible within a human lifetime. This is where wormholes offer a tantalizing solution. By creating a shortcut through space-time, they could theoretically reduce journeys of millions of light-years to mere moments or hours. Imagine the possibilities. This isn't just about reaching another star, it's about unlocking the entire universe. If wormholes were traversable, humanity could explore countless exoplanets, discover new forms of life, and perhaps even encounter advanced civilizations. It would fundamentally change our place in the cosmos, transforming us from inhabitants of one small planet to true cosmic explorers. The implications for resource acquisition, scientific discovery, and even the survival of our species are profound. If our own galaxy faces an existential threat, a wormhole could offer an escape route to a new cosmic home. It's a vision of the future that inspires awe and wonder, pushing us to dream bigger than ever before. Now, let's pause for a moment. If you're enjoying this deep dive into the mysteries of the universe, don't forget to subscribe to our channel and activate the notification bell. This way, you can stay updated on all our explorations into fascinating scientific topics, from black holes to the very edge of the cosmos. Your support helps us continue bringing you these incredible journeys. Moving forward, the idea of traversing a wormhole raises profound philosophical and ethical questions, and one of the most mind-bending is its potential link to time travel. Some theoretical models suggest that if one end of a wormhole were accelerated to near light speed and then brought back, it could create a time difference between its two mouths. This could, in theory, allow for travel into the past. This concept immediately brings up the infamous grandfather paradox. If you could travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. This creates a logical inconsistency, a paradox that challenges our understanding of causality. Physicists grapple with various solutions, from parallel universes to self-consistency principles, where events conspire to prevent paradoxes. The possibility of time travel through wormholes adds another layer of complexity and wonder to their theoretical existence. It's a concept that has fueled countless science fiction stories and philosophical debates, while the practicalities are even more daunting than mere intergalactic travel. The theoretical connection remains a fascinating aspect of wormhole physics. The ramifications of traversable wormholes could be enormous, extending far beyond just faster travel. What would it mean for humanity if we could visit other galaxies, not just observe them from afar? The very definition of humanity might expand as we encounter new environments and potentially new forms of life. Could we encounter alien civilizations, perhaps even more advanced than our own? The Fermi paradox asks why, if life is common, we haven't seen evidence of it. Wormholes could provide a mechanism for such encounters, opening up possibilities for communication, collaboration, or even conflict. The ethical considerations of first contact would become paramount. What technological advancements would be necessary to not only stabilize a wormhole, but also ensure safe passage through it? We'd need propulsion systems capable of reaching the wormhole mouth, shielding against extreme radiation, and navigation systems far beyond anything we possess today. The engineering challenges alone are staggering. Think about the implications for science, communication, and even our understanding of life beyond Earth. Our knowledge of cosmology, biology, and physics would explode. However, there are also dire scenarios to consider. What if a wormhole does exist, but it leads to a hostile environment, a region of space inimical to life? Or what would happen if we triggered a catastrophic event by manipulating such powerful, fundamental forces of the universe? The responsibility would be immense. Moreover, the quest to understand wormholes is not just a theoretical pursuit for its own sake. It pushes the very boundaries of our understanding of physics and encourages advancements in technology that could have unforeseen benefits. The research into exotic matter, quantum gravity, and the nature of space-time itself is invaluable, regardless of whether we ever build a wormhole. Scientists continue to explore the underlying principles of space-time in hopes of discovering new truths about the universe. This includes delving into quantum mechanics, string theory, and other cutting-edge areas of theoretical physics. Each discovery, each new equation, brings us a step closer to unlocking the potential that lies within these cosmic shortcuts, or at least understanding why they might be impossible. The intellectual exercise of grappling with wormholes forces us to question our assumptions about reality. It inspires new mathematical frameworks and experimental designs, even if those experiments are currently confined to supercomputers. This relentless pursuit of knowledge is what drives scientific progress, expanding the horizons of human understanding with every new question asked. The journey to comprehend wormholes is a testament to human curiosity and ingenuity. It reminds us that the universe is full of wonders yet to be discovered, and that our current understanding is merely a stepping stone to greater insights. The answers, whatever they may be, will undoubtedly reshape our cosmic perspective. Throughout history, science fiction has enthusiastically embraced wormholes, portraying them as convenient gateways to distant worlds and exciting adventures. From the Stargate series to the epic journeys in Interstellar and the warp drives of Star Trek, wormholes are a staple of cosmic storytelling. They allow characters to traverse vast distances, encounter alien species, and explore the unknown without the tedious constraints of light-speed travel. While these cinematic representations captivate our imaginations and inspire generations of scientists, they often diverge significantly from the complex physics involved. Hollywood wormholes are typically stable, easily traversable, and often lead precisely where the plot demands. They rarely require exotic matter or grapple with the paradoxes of time travel. The reality, as we've discussed, is far more intricate and yet to be fully understood. The scientific concept of a wormhole is a delicate, unstable theoretical construct, not a ready-made highway. This gap between scientific theory and popular depiction highlights the power of imagination, but also the ongoing challenge for scientists to explain the true complexities of the universe. It's important to appreciate both the inspiration drawn from fiction and the rigorous pursuit of truth in science. Fiction shows us what could be, while science strives to understand what is. The interplay between the two continues to fuel our fascination with these cosmic phenomena. The exploration of wormholes, even if purely theoretical, may one day lead to groundbreaking discoveries about the fundamental nature of space-time, gravity, and quantum mechanics.